Welcome to this seminar on bioenergy and sustainable development. My name is Jim Spaeth, and I'm the current chair of the BioFuture platform. It's my pleasure to be hosting this first session along with Paulo Frankel from the IEA Renewable Energy Division, the head of the IEA Renewable Energy Division. A good day to wherever you are. We're going to have a terrific session today on very important topics related to bioenergy and sustainable development. Those of us that work in the field know that sustainability is a key, very key topic of conversation and a key topic and a key essentially factor that we must always observe when using bioenergy. If I could have the next slide, please. So modern bioenergy is used essentially in all sectors. Welcome, Paulo. In terms of power, heating, cooling, and transport. And it currently is the largest source of renewable energy today, providing approximately half of all renewable energy globally. And it's a very important option for limiting global warming, as we'll hear more about in some of the presentations today. And it's a great option for negative emissions in using pathways and sources like biochar and BECCS. And there's a significant opportunity for the use of bioenergy and biomass to be increased going forward. This session today will explore some of these topics that will help enable bioenergy to be more widely accepted and to address some of the arguments that sometimes prevent bioenergy from being used openly and being considered. We'll also briefly talk about the UN Sustainable Development Goals, which are an important framework for guiding international development in the clean energy space. And we'll talk about biomass supply chains for bioenergy and the broader bioeconomy. There are great opportunities with bioenergy and biomass, and we need to fully explore those and use those going forward to be able to reach our net zero future by 2050, as portrayed by, in particular, in the scenarios of the IEA. And with that, I will offer the opportunity to my co-host, Paulo, to introduce himself. Paulo, please. Paulo, can you hear me? You may be muted.
Sorry, sorry, I have some connection problems. Can you repeat, please?
Yes, Paulo, I was just offering you the chance to introduce yourself, if you would.
Sure. Of course. Thank you, Jim, and sorry for the bad connection. I hope it gets better over time. I'm Paulo Frankel. I'm the head of the Renewable Energy Division at the IEA. I'm also the chair of the facilitator team of the BioFuture platform in my quality, as the IEA serves as the facilitator of the platform since 2019. Thank you, Jim.
Thank you, Paulo. So this is the first of two sessions. Today, we're focusing on bioenergy and climate change mitigation. Tomorrow, the focus will be on sustainability co-benefits of bioenergy beyond climate. I'd like to briefly introduce the four speakers. We have a great panel today. If I could have the next slide. So first, we have Andy Reisinger. He's the IPPC Vice Chair for Work Group 3, and he'll talk about mitigation and some key findings in the role of bioenergy. Then we'll have Sabine Fuss from the Mercator Research Institute on Global Commons and Climate Change, and she will address necessity and regulations options for CO2 withdrawal. Then we'll have Florian Kraxner from EASA. We'll talk about sustainable boreal forest management and challenges and opportunities for climate change mitigation. And finally, last but not least, Annette Cowie from the New South Wales Department of Primary Industries, and she'll talk about key determinants of the climate effects of bioenergy. We will also have a few polls during this workshop. The polls will be through the Zoom channel, so you won't have to go anywhere else. And I would also ask that if you have questions, you use the Q&A, not the chat. Again, please use the Q&A, and we'll be monitoring the Q&A for those questions and have a chance briefly to answer some questions right after each presentation. And then we'll have a long session of discussion of Q&A, 45 minutes or more after all 4 of the presentations. So now I'd like to have you take a look at the first poll, and we will allow a minute for you to give answers. So Ernesto has put up the poll. What do you feel will be the most important role of biomass at the longer term, post-2050? So please select 3 options. It's a multiple choice. And we'll give everyone just a minute to enter their options. So renewable fuel for process heat requirements, or to produce electricity to balance demand with variable renewables, solar and wind, or as a renewable resource for production of chemicals and products based on renewable carbon. Fuels for difficult to electrify transport sectors, such as aviation and marine. Providing negative emissions through BECCS to offset remaining fossil emissions, or to deliver energy services and capture biogenic CO2. And finally, to provide market incentives for more sustainable land and forest management. And in just a moment, we will bring up the results of the poll, and you can take a look at that. And the results are coming in. Looks like as a renewable resource for production of chemicals and products is winning so far. And next, for hard to electrify sectors, aviation and marine. And many of them look fairly close in ranking. So thank you very much for participating in the poll. We just wanted to get you warmed up because we want this to be a very interactive webinar and working group. So now I'd like to introduce the first speaker. It's my pleasure to again bring on Andy Riesinger, the IPCC Vice Chair for Work Group 3. Andy, the floor is yours. Thank you.
Thanks very much, everybody, and good morning, good afternoon, good night in my case. I'll just bring up my slides. I hope you can see them. So I'll attempt to give a very brief overview of some of the key findings from the recent assessment report by the Intergovernmental Panel on Climate Change and Mitigation, but with a particular lens on bioenergy. And any such presentation is necessarily subjective in terms of what I pick, and I would encourage you to actually dive into the underlying report to get more of the details, which are comprised in the range of chapters and the summary products. So let's start with some generic bad news and get those out of the way. As you're probably aware, greenhouse gas emissions have continued to rise globally, and they're now at the highest level in human history. The last decade has seen decadal emissions higher than ever before. And you can see those trends occurred in all major groups of greenhouse gases, carbon dioxide from both fossil fuel use and land use change in forestry, methane, nitrous oxide, and fluorinated gases. And on the right-hand side, you can also see the actual modeled warming attributable to each of those groups of gases, which you can see broadly mirrors the emission trends with a slightly higher contribution from methane. But there are important signs of progress. It's not all bad news looking at emission trends. Some of those key elements of signs of progress include the rapidly declining costs of some technologies, especially solar PV, wind, battery storage, which correlated with an increasing, rapidly increasing installed capacity of those technologies. We also have increasing climate policy coverage, both framework legislation, net zero targets, and carbon pricing schemes. And last but not least, we have seen sustained reductions in some countries. More than 18 countries, depending on when you start counting, have managed to reduce their overall greenhouse gas emissions in the absence of economic crises, largely by decarbonizing energy supply, improving energy efficiency, and also addressing energy demand. So a way of summarizing this would be to say simply, climate policy works. We have evidence that it works, and that's an important finding. Collectively, these actions have avoided several gigatons of greenhouse gas emissions, which also means that the highest emission scenario used in modeling studies, RCP 8.5, is no longer business as usual. This is important good news. It's proof of concept, if you like. However, we are starting from a low base. We apply policy narrowly, inconsistently, and with insufficient ambition and finance. That's why the greenhouse gas emission trends are what they still are. So what do we need to do overall? It's very clear that unless there are immediate and deep emission reductions across all sectors, the goal of limiting warming to 1.5 degrees Celsius is beyond reach. And that can be illustrated by the emissions gap figure, which you've seen before from various other publications. The red line shows the global greenhouse gas emissions under currently implemented policies. Current NDCs, so that's the national determined contributions under the Paris Agreement, achieve a stabilization roughly of current global emissions, but no significant decline. If we wanted to limit warming to 1.5 degrees, by 2030, global greenhouse gas emissions would have to be far below where they are currently indicated in the light blue line. And the simple fact is, unless we have a rapid drop in greenhouse gas emissions this decade, limiting warming to 1.5 degrees is simply no longer likely possible. In fact, it becomes unlikely that we manage to limit warming to 1.5 degrees. That would entail significant greenhouse gas emission reductions of about 43% by 2030 for both CO2 and, importantly, also for methane. Limiting warming to 2 degrees with at least 2/3 probability is interestingly not infeasible, even if we stick with current indices. That's illustrated by the purple band, but it would rely on a rapid acceleration of mitigation after 2030, which is in itself both challenging and, I guess, straining sometimes political credibility about this massive shift that magically happens 10 years from now. Whereas immediate reductions, as illustrated by the green lines, would offer a much more gradual decline and therefore a higher feasibility of actually achieving the goal of limiting warming even just to 2 degrees. So we don't have a minute to waste to accelerate mitigation actions if we want to achieve those temperature goals. Fundamentally, what do we need to do? This message has not changed in the IPCC sixth assessment report. We need to achieve deep emission reductions of all greenhouse gases, particularly reaching net zero CO2 emissions in the 2050s for 1.5 degrees or by the 2070s for 2 degrees. But reductions of other non-CO2 gases are also a critical component. And it's also important to point out that the chances in model pathways of limiting warming to 1.5 degrees are now lower than they were back in 2018 when the IPCC produced its previous report, especially on limiting warming to 1.5 degrees. That's because emissions have continued to rise. We're therefore now starting from a higher base and with a higher warming from the emissions that occurred over the last 3 to 4 years. In other words, actions, or rather in this case, inactions, have consequences. The chance of limiting warming to 1.5 degrees is slipping from our fingers as we speak. Nonetheless, there are a range of pathways by which we could achieve net zero greenhouse gas emissions, which are, as I just pointed out, a prerequisite to limit warming at 1.5 or at 2 degrees. And those bar charts show some of those alternative choices relative to the current sectoral sources of emissions on the left-hand side. They have a common feature. All pathways that achieve net zero CO2 emissions have almost zero carbon electricity by 2050, especially if you're aiming to limit warming to 1.5 degrees. There are other important choices, though, in different scenarios explored, and that's important to be aware of to avoid falling into a trap of thinking there's only one way of achieving climate change objectives. Those scenarios, and that's illustrated by the small bars in the bottom, which are different illustrative pathways for how to limit warming, they have a different balance of supply and demand measures. They differ in the deployment of CCS or the accelerated use of renewables. They differ in the amounts of non-CO2 emissions, which lead to an additional contribution to global warming. They also differ in their balance of carbon dioxide removal, CDR, versus gross reductions. And they also, post the net zero date, show a different reliance on net negative CO2 emissions, which is important to recover from a temperature overshoot. Only about half the scenarios assessed by the IPCC actually achieve net zero greenhouse gas emissions. Half of them stay much closer to net zero CO2 emissions, which means we don't bring temperatures down after they peak. These are all important scenario choices driven by either choices in the design of scenarios or by assumptions and models about what the most cost-effective solutions to limiting warming are. So let me now explore a little bit more what those scenarios show for bioenergy in particular. A common feature is that all deep mitigation scenarios, as shown on that slide, involve a rapid increase of low carbon energy in primary energy, and as part of that, of the use of bioenergy in primary energy. So the blue bars are for 1.5 degree scenarios, and the other bars are for scenarios with slightly higher warming. So you see that bioenergy use increases in all of those scenarios that achieve temperature goals very rapidly from 2030 onwards, except for those that barely manage to limit warming to 2 degrees, with further increase towards 2050. But they also show a very wide range, and I want to explore the origins of this very wide range. So the bioenergy use in 2050 in 1.5 degree scenarios could range from 15% to more than 35%. That's a massive scaling uncertainty that we need to understand more. One is that as the IPCC explored a range of mitigation pathways, it's very evident that the land use change, especially for dedicated bioenergy crops, differs widely among different scenarios. On the right-hand side, you see land use changes in 3 illustrative alternative mitigation scenarios. On the left-hand side, the negative 2.0, it's a scenario that limits warming to 2 degrees, with a heavy reliance on net negative emissions towards the end of the century, with a massive upscaling of land use for bioenergy. Whereas the middle scenario, focusing on renewables, has a very moderate expansion of bioenergy land and much smaller land use overall, because it relies heavily on the rapid acceleration of other forms of renewable energy. Whereas the sustainability pathways scenario on the right-hand side has a more mixed approach to those land use options. And so overall, the bar charts on the left-hand side show the amount of modeled land use change for energy crops in different scenarios that limit warming to different levels of temperature. Again, you see a wide range in the modeled outcomes, but all show an increase in the use of bioenergy crops. Of course, one needs to add, and I think Annette will talk to that, that integrated assessment models are not necessarily the most skilled tools to explore more nuanced integrated land use options that tend to have a solution for either bioenergy crops or other forms of land use. And one of the challenges is, can we do both? Another important role for bioenergy is, of course, the ability to withdraw carbon dioxide from the atmosphere that Sabine will talk about. So carbon dioxide removal, a key finding from this report, is in fact unavoidable to counterbalance hard to abate residual emissions if we want to achieve net zero CO2 or net zero greenhouse gas emissions. We cannot do without carbon dioxide removal sustained throughout the 21st century after reaching net zero, because we cannot reduce all gross emissions to zero. If we have a net zero target, we must deploy CDR, carbon dioxide removal, to help us meet that target. And that's only a slow realization in some areas of policy. This is in fact a necessary condition. But I don't want to stop just at that one particular use of carbon dioxide removal. The IPCC report in its chapter 12 has a comprehensive box on the roles of carbon dioxide removal, and it identifies essentially 3 different types of uses. In the near term, carbon dioxide removal can simply accelerate the reduction of net emissions than what would have been possible by focusing on gross emissions only. In the midterm, as I already said, carbon dioxide removal is essential to counterbalance hard to abate emissions in order to achieve net zero targets. And in the long term, we may want or need to deploy carbon dioxide removal to achieve net negative CO2 or greenhouse gas emissions, which are a requirement to help us reduce temperature after a peak. And that is, of course, one and increasingly the more likely pathway if we want to limit to 1.5 degrees at all is by overshooting it in the near term, given our lack of ambitious climate action, and then try and draw temperatures down again, which is of course essential to limit long-term sea level rise, for example. I very briefly want to touch on the interaction with Sustainable Development Goals, realizing you have a whole day on this tomorrow. The report has done a synthesis of interactions of particular mitigation approaches with the SDGs. And I just want to highlight some of those findings for bioenergy and renewable supply. And I guess what strikes me out of that is that the literature offers a decided ambivalence about whether bioenergy and renewable supply from agriculture and forestry has a positive or a negative interaction with many SDGs. The answer is always, it depends on context and on the way options are implemented. And that is the challenge for you as a group and for us as a whole, how to ensure that those round dots which illustrate a ambivalent outcome become pluses, i.e. known co-benefits with Sustainable Development Goals. So that raises the question, there's, as you're all aware, a lot of concern about, well, is bioenergy a solution or is it in itself a problem? And there's no easy answers to that, and the IPCC report offers a whole range of lenses of potential entry points. One is, of course, it always depends on scale, and that's both linked to the opportunity cost and the carbon debt from rapid deployment of bioenergy that displaces other land uses that could also have stored carbon. And of course, critically, the competition with both food security and biodiversity. These are largely driven by scale. It also depends on context. What are, in any given place, the existing and the alternative land uses that could have been done instead of bioenergy? But also, what's the governance? How are indigenous rights being treated as part of deploying bioenergy? These problems can occur even at small scales. They're not necessarily only scale dependent. But then, of course, there's also the question around the strategic role of bioenergy. How is bioenergy going to be integrated with the energy system, with land, so food and biodiversity systemic approaches within land use? What are the teleconnections? What is the consequences of bioenergy deployment in one part of the world on other parts of the world? How are supply chains being managed to ensure beneficial outcomes across the globe rather than trade-offs from one region to the other? And what's the role of bioenergy, and in particular, more ambitious uses of bioenergy linked to carbon dioxide removal, for example, for the mitigation portfolio risk profile? Are we displacing taking necessary urgent near-term actions by relying on future solutions? Or how are we using the undoubted potential of bioenergy to remove carbon dioxide at scale in the context of near-term policy choices we have to make? These are just some examples where bioenergy needs to be driven by a clear vision to ensure beneficial outcomes across a number of dimensions. So to conclude, a very personal attempt at a summary that's of course based on the IPCC assessment, but are my personal views, if you like. One is it's unambiguous that bioenergy is highly versatile with strong potential for co-benefits if it's integrated well across multiple dimensions and scales. And that's evidenced by the fact that bioenergy, also in the IPCC report, crops up in a whole number of places. It cannot be confined to a single place because it has so many potentially widespread uses. However, the credibility of if implemented well does reduce with scale. And but even that is not a full answer, because significant harm could occur even at small scales if not implemented well. See governance, see indigenous land use rights, see what does it do to policy ambition overall at national scale, for example. And of course, what's small scale and what's large scale remain highly qualitative terms. If a particular island wishes to deploy bioenergy, the definition of large scale may be, a few thousands of hectares, whereas in other countries, a few hundreds of thousands of hectares might still be considered mid-scale. it is clear from a range of studies that look at sustainability constraints on biomass, there's unlikely enough sustainable biomass to allow bioenergy to serve all possible purposes that it could in theory be useful for. So how are we going to prioritize? It is also clear that the risks increase with both scale and the rate of implementation. So policy consistency and continuity are critical in any case in order to provide a gradual ramp up rather than a rushed run, which inevitably leads to a rushed plummeting of policy support if they turn out to be not well chosen. There are critical interactions with food systems via land sharing and sparing and land system governance that determines biodiversity co-benefits or trade-offs. So a strong integration of biodiversity of bioenergy deployment with those dimensions is, in my view, critical to achieve positive outcomes. And finally, it is important to remind ourselves that current investments in technology development and deployment, but also in governance, in MRV, that is monitoring, reporting, and verification of the climate benefits, and policy support and integration, especially with those other dimensions, they are critical, but currently our efforts in those areas do not match our stated climate ambitions or, in fact, our reliance on bioenergy to help us achieve climate goals. So that's my very rushed attempt to provide some insights. I would encourage you to simply dive into the full assessment report that's published and form your own view and use this as a resource for your own work. Thanks very much.
Andy, thank you very much for that comprehensive, quick look at so many complicated issues related to bioenergy. That was a great coverage, and I look forward to studying your presentation more closely. A few questions came up, and of course, there are many questions that could be prompted by your conclusions and your results, but one quick question, not really a quick question, but a question that came up is a challenging one. Do you have any advice on how to confront the food versus biomass issue?
Not really advice, but one of the key conclusions in my view is from the food perspective that demand side measures are a necessary element because, as I said before, I mean, you can look at land as a finite resource, and the question is, how do we both service bioenergy demands and food demands? If we rely on lots of extensive land uses for food production, there is not enough land, and bioenergy will always encroach on food producing land. More integrated food systems and demand side changes are a prerequisite, in my view, to enable us to no longer need certain types of land to produce food because we have other sources of food to allow us to use that land for bioenergy use. So it's the coexistence can of course be achieved by more integrated land use. That's one way, but the question is always, how do you achieve this at scale? So there's different dimensions. You can have more integrated land use at smaller scale, but from a planetary perspective, I think without achieving some demand management involving dietary change, involving reduced food loss and waste, there is too much land that's used for food production, which does jeopardize the livelihoods of those producing food and those relying on the food on those lands. We need to find ways collectively to no longer rely on low productivity lands to produce limited amounts of food, but to actually free up those lands. But it cannot be at the expense of those who rely currently on their food production on that land. That's the livelihoods of producers and the people who rely on that food for their own consumptions. It's not a simple solution, but overall, I think that's that integration between food systems and bioenergy deployment, I think.
Well, thank you, Andy. Yes, a topic that needs a lot more focus. Appreciate it. So before I go to the next speaker, I'd like to acknowledge those that really sponsored this webinar, a couple of webinars. This was really led by the IEA Bioenergy Technology Collaboration Program, and as well as co-sponsored by GBEP. And I appreciate speaking for the BioFuture platform that we were also invited to co-sponsor. So the three organizations bring this together. These topics are of critical importance to all three of our organizations. In particular, I'd like to acknowledge Luke Pelkmans, the technical coordinator for the TCP, that worked very hard as the person that really catalyzed this webinar and put it all together. Thank you to Luke. Now I'd like to introduce the next speaker, and that'll be Sabine Fuss, who will talk about necessity and regulatory options for CO2 withdrawal. Sabine, please.
Well, thank you for the kind introduction, and I'm sharing my screen now, which I hope you see. Let's make it big. Great. All right. Yes. So Andy did a very good job setting the whole context, so I can save a lot of time describing what the role of CO2 removal in 1.5 and 2 degree pathways is. And basically, what you see in these pathways from the latest Working Group 3 contribution to the IPCC 6 assessment report are the three things that Andy already mentioned: this immediate turnaround in emissions trends, drastic and deep reductions already by 2030, then net neutrality by between 2050 and 2060, and then we dive under the zero line in the second half of the century, meaning that we withdraw more CO2 from the atmosphere than we're emitting back to it. And you actually see that this happens for almost all of the pathways that bring us to 1.5 degrees at the end of the century, or even 2 degrees. So this is really why we're talking about a necessity here. Carbon dioxide removal is becoming necessary to achieve ambitious climate targets, and that should also not come as a surprise given how late we are with mitigation. Now, what's behind those pathways? My job is to dive a little bit behind the scenes, and models, especially the integrated assessment models that underlie most of these pathways that Annie has also been showing, have been focusing quite a lot on combining bioenergy with carbon capture and storage, even though they have been expanding their portfolio of CDR already a little bit more as of late. And I guess I don't have to tell you that both in the case of bioenergy and in the case of fossil carbon capture and storage, the best we could ever achieve is neutrality. So basically, only if you combine the two concepts and don't let the CO2 that you previously captured in the additionally grown biomass back to the atmosphere, but instead capture it and store it underground, you can actually achieve a net negative balance and withdraw CO2 from the atmosphere on a net basis. So that's behind what's behind most of those net negative pathways. A lot of the models also incorporate afforestation and different improvements in agricultural practices right now, and parts of them also direct air capture. But still, this is what most of the debate has been centering around ever since AR5. Now, we did a systematic literature review of the costs, the potentials, but also actually the side effects of upscaling bioenergy with CCS in those pathways. And we found that there is really a great emphasis in the literature on the negative side effects, particularly to do with the land use changes associated with withdrawing large amounts of CO2 through BECCS. I mean, what we saw also in these pathways and also in the picture that I've shown is like 10, 20 gigatons CO2 at the upper side of the spectrum. And at these scales, of course, the question is, where do you plant all this biomass? And doesn't that threaten our other policy goals that have to do with biodiversity conservation, feeding a growing population, and so on? Interestingly, in a similar exercise we did later on with Pete Smith, mapping different land-based CDR options against the SDGs, we found that for afforestation and reforestation, that's what you see on the right-hand side, there seems to be a lot more also on opportunities. So while this sort of negative representation of back side effects in the literature doesn't need to mean that there are not also opportunities. It's basically coming from exactly what Andy has been showing us too. And I've also taken the SR 1.5 scenarios here in order to highlight it a little bit more. So what you see circled in red already 1.9 watts per square meter pathways. And indeed, you see vast conversion of pasture, food and feed crops areas, and an increase in the areas dedicated to energy crops and also forests to sequester additional CO2. There's a wide range, of course, and Andy has spoken nicely to the assumptions that are behind those different ones here, so I won't repeat that. But still, this goes a long way showing what is actually fueling this debate and raising the skepticism. However, what Andy has also been touching upon a little bit is that often these models that generate these pathways are not very nuanced, and they don't that doesn't only apply to the land use issues that he's been putting on the table, but it also comes from sometimes not picking the low-hanging fruits that you would actually see if you zoom in to national or even local scale. And I brought you here a case study from Sweden, and please only look at the right-hand side, at the right map, where you see the larger installations, industrial installations of Sweden, nicely located at the coastline, by the way, as well. And you see that you have quite a few installations here. And the nice thing about it is that most of them are already using partially or even fully biomass as a feedstock, and that actually enables them by simple retrofitting with CCS to immediately go negative without sacrificing another hectare of land, because the biomass already comes from their own national supply from the forest industry. So this actually means that if we add those things up and the purely biogenic point sources you see here in green, then you come up with a marginal abatement cost curve that achieves a lot of the removals even at a cost of less than 100 euros per ton of CO2. And if you would sort of integrate that, then you would see that adds up to more than half of all the Swedish emissions from all the sectors. So I think this goes a long way to show that we also need more bottom-up research in order to identify opportunities, as Jim also said in his introduction, and not only focus on the trade-offs. Another thing that I want to put up as a caution is that if we focus in our criticism too much on BECCS, then we are losing sight of the fact that a lot of the issues are actually more tied to bioenergy. And so integrated assessment models that have been trying to constrain BECCS in response to these concerns, they actually still do end up with a lot of bioenergy, because bioenergy is just such a versatile technology. And if we can't offset emissions by removing CO2 from the atmosphere, then we will need bioenergy in other hard to decarbonize sectors, such as transport, for instance. And this is exactly what you see here. You may end up with even more bioenergy and ambitious climate stabilization pathways if you constrain BECCS. Now, how do we regulate that then? So in principle, if you consider the climate as a public good, we're actually asking people and firms to perform a service here and clean up the atmosphere for which we don't pay them. So it's a classic market failure, and that signals the need for policy instruments. What we actually need is incentives to honor removals reflecting the societal benefit, for instance, in terms of avoided damages, but also having more flexibility to stay within the carbon budget. And CO2 pricing can actually be an effective instrument to incentivize the CDR scaling, whether that's done in an emissions trading system or through taxation or reverse auctions or whatever is a different question. But in principle, CO2 pricing enables you to find the cost optimal CDR portfolio. And then if you also have comprehensive carbon pricing that extends to other sectors, for instance, also the land sector, then you can also reduce problems such as indirect land use change, where you normally would also expect some leakage. However, incentivization is one thing. There are other externalities, and Andy pointed to those already quite extensively. So that needs accompanying regulation. In a recent paper that's so far only available in German, sorry about that, but we're working on an English version. We try to systematically go over the different options to withdraw CO2. And you also see quite some heterogeneity over the different externalities that we identified here. So some apply more to land-based options, some more to the ones around geological storage. And that also means that we will need a portfolio of regulations in order to contain those externalities. Just picking out one example, because I have little time, is innovation. So technological processes deemed still quite expensive for the foreseeable future, especially comparing that to current CO2 prices. But an expansion may make, nevertheless, a lot of sense, because we want to realize innovations and learning effects. Credible CO2 pricing might also trigger that. But we might want to go down the learning curve a bit faster and create niche markets at an early stage, similar to the EEG at EU level, for instance. So you could have an additional subsidy on CO2 prices. You could work with quantity instruments, with technology portfolios to enforce critical market sizes and diversity. Across technologies, you could have targeted R&D projects that you finance for industry and research institutes to work on specific problems, and all of that under the premise of eventually phasing that out as CO2 prices rise and take over. You can have a similar analysis for the other externalities that I had in the matrix, but let me rather spend my last minute on a debate that I think is quite important, and that's the focus that many countries and regions, actually including my own, have had. Which is a tendency to focus on natural climate solutions. So I already said there's already in the literature quite a focus on the negative side effects. Similarly, the debate in many countries has been to favor land-based expansions of the terrestrial sink, for instance, through afforestation, for instance, through improved agricultural practices, to offset residual emissions. And if you look at that picture here that shows costs versus potentials, that makes a lot of sense, right? You have here technologically mature options that are also relatively less costly if you compare it to the others. There may be co-benefits if you implement them in a clever way, and that also means less public resistance, which also means often then more buy-in from politicians. However, there are also some concerns if you have a second look. So a concern that's often brought forward by NGOs especially is that, these credits might be cheap. If we put them into an emissions trading system, they might undermine more costly emissions reductions. Also, they are often less permanent, and the risk of reversibility is higher if you think about ongoing climate change and disturbances that come along with that. And we'll have a whole talk following on that afterwards, so I'll not say much about that. Monitoring, reporting, and verification challenges might be a lot higher, despite advances in combining remote sensing and in situ measurements. The land footprint can actually also be quite high. There could be resource constraints and land-based leakage. I already pointed to that before. Also, the need to address distributional impacts, right? If you set aside a lot of land for carbon sequestration, what does that mean for land prices? How will that affect food prices? This is a topic getting ever more sensitive also in the current geopolitical situation. So to wrap up, I want to leave you not with a lot of challenges and question marks, but also a couple of ideas for how to approach addressing those challenges. So for the unwanted interactions between mitigation and removal, I would say you could separate targets. So CO2 pricing can work via a separately determined price for mitigation and for removals, or by separated quantity targets, or by having separate carbon markets for this. Land-based leakage, you could have a phased approach. You could first focus more on measures that do not increase the demand for land that much, that the land intensity being lower. In the medium run, then go to border carbon adjustment like policies for land-based leakage that could also then cover, for instance, biodiversity impacts. And in the long run, of course, we need to seek global cooperation, especially as we're also talking about trading international offsets. For the distributional impacts, a better understanding first is needed of those impacts. The dynamics of asset values, especially of land, but maybe also here we could have a phased approach, or maybe pilots with restricted coverage, enabling us to learn more about monitoring, reporting, and verification, the speed of technical change, permanence being a big issue, the dynamics between permanence and incentives. You could, for instance, allow also less permanent options into emissions trading, but then adjust the incentive, the carbon price, by a discount factor based on its half-life, and so on. So this is just to throw out a couple of nuggets to also incentivize the discussion. And I want to thank you for your attention and close.
Sabine, thank you very much. Another very interesting presentation. Question for you. Can we actually measure land use change caused by bioenergy these days?
I think this is one of the things that also the contribution of the third working group to AR6 now has shown quite well, how difficult it actually is to actually get an account of emissions from land use change. And I think that's something that we need to work on, obviously. But also here, if you implement policies on the basis of this, then you have different options, right? You could, for instance, also enact policies and incentives based on the measures, right? So if you plant so and so many trees, for instance, then you get compensated for that. So that might be something that you could already start with while you're improving on the first part.
Thank you, Sabine, very much. And we look forward to more questions in the follow-up panel. So now I'd like to ask Ernesto to bring up the second poll question. Brought up previously, but we're going to open it again. So how should forests be managed to achieve the highest climate change benefits? Just select one answer, please, and then we'll bring up the results. And here are the results. Clearly, this group favors best management practices. Not a surprise there. So now we need to apply a lot of work to make sure that we do use best management practices and that we educate all on what those are and continue to develop those going forward. Thank you very much for the second poll and for participating. So our third speaker today is Florian Kraxner from IASA. He will talk about sustainable boreal forest management and challenges and opportunities for climate change mitigation. So Florian, please take it away.
Yeah, thank you, Jim, and hello, everybody. Interesting questions you're pulling up here. Actually, also difficult to answer, but let's see if I can shed some more light in this discussion. I've been asked to provide some insights on the forest and forest management topic. For instance, should we protect more forest or should we intensify? And our International Boreal Forest Research Association had a report done on that, just published end of last year. And it was an effort across 6 boreal countries, including Russia. This is something which at the moment, understandably, wouldn't be possible anymore, but we had 25 authors from all over these countries, and we applied it, or we had a methodology that mimicked a little bit IPCC. And we had internal and external reviews, and as I said, published report only shortly, and you can download it at the IPFRA webpage, www.ipfra.org. And since there are many authors, I thank those like Peter Höchberg or Werner Kurz for borrowing their slides. Yeah, well, how can forestry in the boreal region contribute to climate change and mitigation? And yeah, most important is, for instance, in everybody's mind, afforestation. So by enhancing the carbon stock in forest ecosystems, by providing raw material for long-lived carbon-containing products, or by providing, for instance, raw material for products substituting fossil carbon, which includes concrete production, energy-intensive products such as steel, which can be produced with biomass, etc. We are concentrating, however, on this carbon stock enhancement in forest ecosystems. And what we did is we compared the carbon stocks of the boreal forest from 1990 to 2017 in these 6 countries: Russia, Canada, the US, and the 3 Nordic countries by size of contribution to the boreal forest here. We assumed that the forest area did not really change over that time. So what is and where is the boreal forest? Here's a little bird's eye view, and we see a map here, particularly or especially produced for this insight report by IPFRA. And you can see the unmanaged forest in green and the managed boreal forest in blue. The managed forest is a little bit overrepresented since for statistical reasons, we had to also include area that is not yet managed, but designated managed forest area. And you see, the issue is here that a lot of the warming will happen in these Arctic areas in the Nordic countries and the circumboreal area. And we see here the mean annual temperature, how we have been used to it between the late 70s and 2013. Versus now on the left-hand side, the temperature distribution, where you see a lot of area in dark blue, where the average temperature, annual temperature, is still around -15 degrees or -10 degrees, and very little actually in red, which means that there are positive average temperatures. On the right-hand side, annual precipitation on average. Red is very low precipitation, around 100 millimeters per year, and blue is quite a lot, around 1,000 millimeters per year. If we compare that now with the 2070s projections under RCP 8.5, we heard from Andy, this is not anymore the track on which we are on, but almost. Here's the comparison, and we see particularly in the temperature on the left-hand side that we are massively warming the area up. Everything is getting more reddish. That means there's hardly any area left that is below 0 degree on average. And not so harsh, we can see on the right-hand side precipitation. However, the patterns are changing and the area is changing, even if the same amount of precipitation is falling. So much to the temperature in this area. What we had to do in our assessment is to deal with very different data sources, meaning, for instance, that we had for the Nordic countries, Norway, Sweden, and Finland, long-term information at very high resolution versus On the other hand, for Alaska, Canada, and Russia, we had a rather low resolution and had to work with some aggregate figures. However, we managed to harmonize each and everything as good as it gets and came up with this basic table, which actually looks very simple, but is the first thing of its kind that has been made for the boreal areas across the borders of these 6 countries. And you see the figures of total forest area distributed between Alaska and Russia, with, of course, Russia up to 800 million hectares of forest compared to, for instance, Canada, 160 million hectares. Norway and Sweden between 10 and 30, and similar in Finland. You also see a lot of asterisks here that show that we had to balance between different information material, between different years where we could obtain the data, etc. So we, as I said, we tried to harmonize this as much as possible. The second column shows the carbon stock above ground in living trees in million tons of carbon, which varies again between in Norway about 355 million tons hectare stocking there, and a huge amount, for instance, in Russia with 31,000 megatons carbon stocking there. And the carbon stock per hectare, which you can see is varying in the right column between 30 and 48 in a more extreme case for Canada. In Canada, also managed and non-managed forest areas are mixed here in this information, so it's not so much varying actually. Okay. From this basic information, we move on. You see in the left, on the left-hand side column again, this 31,000 megatons for Russia, the total stock, so to say, for Alaska, 800 megatons carbon. But what is interesting is on the right-hand side, what has been removed in terms of carbon and megatons carbon per year. This is, for instance, nothing in Alaska because we assume that there is no real forest management ongoing. 24 million tons carbon, for instance, in Canada, about the same in the Nordic countries like Russia, 37 megatons. The Nordic countries in this case aggregated and compared with Russia, about the same removals, so the same amount is harvested in the 3 Nordic countries like in the entire Russia. If we go to the further right columns, we see that there is a percentage carbon removed by harvests per year. And this is corresponding to it, but maybe even more interesting now what is taken here from the fire. Forest fire takes about 0.6% of the area in terms of carbon, and this is quite huge. Let me look a little bit further into that one. We see on the left-hand side a quite famous 2015 science paper which indicates the forest fires, again in this bird's eye view between 1997 and 2014. And this gives very interesting information. It doesn't say, for instance, that since then we see more and more that normal wildland fires, which we considered not stand replacing in former times, are moving towards becoming more severe and become stand replacing. That means that a lot of carbon is emitted through it. It's not only a ground fire, but it's a crown fire where also the trees that are affected are dying. Interesting little graph to the right-hand side for Finland and Sweden. It's historic from 1500 up to basically now, and we can see that almost 1% of Finland and Sweden was burning over a long historic period until basically a modern forestry set in between 1850 and 1900, which drastically lowered the forest fire and the sacrifice of, so to say, area towards forest fire, but also emissions here. So management seems to make a big difference here. Just a short excursion into forest fires. So projected burned areas for Russia under different RCPs here. I pick Russia because it's the largest country in the boreal forest. So we can see that if we have burned area in the dimension of 4 million hectares per year now, under the RCP 8.5, we will end up by the end of century more or less around 3, maybe 4 times higher areas that are prone to burn. All other scenarios, except for the 2.6, which is more or less aligned with the Paris Agreement, also face quite some increases. And even with the 2.6, RCP 2.6, we see a slight increase, which is due to the delay effect in warming, and then leveling out again so that we more or less stay the same. Of course, we can also look here a little bit into a possible future where most of the fires are occurring in the boreal forest, and dark red dots mean that on average per year 25,000 hectares are burning, 25 to 50,000 hectares in this very pixel, in this area. So similarly, I must say, we have global projections, and here where we start presently at around 90 million hectares burning per year, then we might end up on global levels at 200 or even more million hectares burning per year on average. And we see a similar pattern here. That only with RCP 2.6 we will end up at the end of the century at no more area burning, still having quite a curve here, which means that we are suffering some increase, which then might go back. All other scenarios here show more intensive fire activities. And this is a map that shows where this is most likely to happen. So a lot of area is affected, of course, in the boreal and on the northern hemisphere, but largest fires are to be expected, or highest intensity and hotspots are to be expected actually in the tropical areas here, the Congo Basin, then central Brazil, Cerrado possibly. Yeah. Okay. But what does carbon stock management mean for us? What did we observe, and how did we compare that? This is interesting for the 3 countries, Alaska, in this case, US, Canada, and Russia, where forest management is not so intensive. As we have seen for a large area like Russia, the harvesting activities are only as high as in the 3 countries combined, in the Nordic countries, and also in Canada, harvests are minor. In Alaska, we see the carbon stock is more or less keeping constant, maybe losing even a little bit in terms of megatons carbon. In Canada, the green part, this is the carbon stock, is also maintaining its dimension, and there is a little bit of harvest which is indicated in yellow. And in Russia, please note that we had to change the scale, the y-axis here, in order to make it all visible. We also maintain the carbon stock more or less in the same dimension and have comparatively little harvesting on it. And now if we look into these countries which are much more intensively managed, this is Norway, Finland, and Sweden. And we can see that in all these countries, the carbon stock is clearly increasing, while at the same time harvesting is also increasing. And this is, of course, a very interesting development here. What we can say, and for the example of Sweden, if we assume this 1,000 megatons of carbon as the baseline in 1990, where we started this off, basically the amount of carbon sequestered above ground, this is quite strongly increasing. So we end up at around 1,250 million tons. Plus we had a massive harvesting increase. And if you calculate this cumulative harvesting amount and the biomass carbon increase together, this is basically what has been removed from the atmosphere. And what then happens out of that, this depends very much how you use it. If you go into long-term products, for instance, furniture or other wooden products, or if you turn it into pulp and paper or bioenergy, something in between, if you use a cascadal approach or not, this depends very much how much of this removed carbon from the atmosphere is again released into the atmosphere and how fast. And what we can also say here at the example of Finland is that both over time, the age of the tree became, the average age of the trees became relatively younger, while at the same time the volume, the stocking volume per hectare increased. And the same is also the mean annual, with respect to the mean annual increment, that we can observe a very strong increase of the mean annual increment, meaning the growth rate, while the age of the trees went back. So the trees became massively younger, which also is a sign of very active management in Finland. So what about the carbon in soils? Also in soils, we could observe that actually in all areas, the carbon content increased slightly. So no matter if there is intensive or rather extensive management. However, what we could also observe is that this is not the case where there is forest stocking on wetlands, and particularly where there are large-scale removals and clear cuts. And with that, let me come to the conclusion. So it is very interesting to show that we have basically three different systems of management here in the boreal forest. We have the very intensive management in the Nordic countries. We have a much less intensive management in Russia. And we have in Russia and Canada, I have to say, and we have basically no management in Alaska. The interesting thing is that particularly where there is no management, like in Alaska, and partially also in Canada and in Russia, we are losing carbon, stocking carbon in the biomass. And where there is a relatively intensive carbon management in the three Nordic countries, we are gaining carbon in the stocking biomass, in addition to all the harvests which you take out earlier, of course. So the reason is that most of these additional losses in Alaska, but also in Canada and in Russia, are due to very heavy forest fires. And as I have shown a little bit with the help of some climate figures and also the trend of fire hotspots in the area, this is not getting less. We will have to face more forest fires, particularly in non-managed areas, but also in managed areas. And we will have to face more intensive fires. So moving from ground fires to ground fires. which of course generates a lot of emissions. And in that sense, it is of course a little bit strange that we only had one chance now to decide in these questions in the opinion poll that you put up. Either you protect, for instance, or you harvest sustainably, or you protect against forest fires, but you could not mix these three measures. And I think this is exactly what we need. We need action according to what Andy Reisinger showed in the first presentation. We need these negative emissions with the help of land and forests that Sabine showed, and we need a very careful forest management, and management is not bad. This is what the figures show. If you want to see and hear more, we have our next, the 20th IFRA conference next year in Finland. And thank you very much.
Fine, thank you very much. We have a number of interesting questions, but I'll just take one at the moment and we'll do more during the panel. How does the loss of forests through fire compare to the loss through diseases such as pine beetle kill?
Yeah, very good question, because one shouldn't even talk about forest fire when talking about disturbances. Also, the pine beetle losses are getting more and more, and there are also other diseases or other pests that take over. So we have seen this massively in Canada, where everybody thought that the pine beetle will not jump the Rockies, but it did, also due to warming climate. So the opportunities are much bigger. Still, forest fire areas are bigger, and there is an interaction between damaged forests and weakened forests by climate, but also by, for instance, bark beetles. And we have been seeing now massive bark beetle attack in Central Europe on spruce. So we will most likely lose spruce towards more northern countries or higher elevations. And there is massive bark beetle and other pest attacks in Siberia, which comes almost close to the areas that are burning on an annual basis. So we have to really think about how we manage that in the right way.
Thank you, Florian. Very interesting, and more questions to come. So now I'd like to introduce Annette Cowie, who is not a stranger to most of us. It's a pleasure to have Annette on this panel, and she'll be talking about key determinants of the climate effects of bioenergy. Thank you, Annette.
Thank you very much, Jim. I hope you are seeing my screen now and will shout if there's some problem with it. Thank you very much for the opportunity to speak at this event. I'd like to start, in case I forget at the end, to acknowledge the input to this presentation from, in particular, Göran Fernandes, who's the leader of Task 45, and also the other participants of Task 45 and the earlier task, Task 38. These are tasks of IEA Bioenergy. There we go. As Andy and Sabine have clearly outlined, in order to achieve the temperature goal of the Paris Agreement, the world will need to reach net zero in the second half of the century. That's net zero CO2, actually, as Andy explained. And that's a condition where emissions are balanced by removals. And there are several ways that bioenergy can contribute to achieving this balance. Bioenergy is a renewable energy source that can displace fossil fuels, so therefore reduce fossil fuel emissions. It is essentially carbon neutral as long as the biomass is regrown after harvest, apart from any fossil fuels that are used along the supply chain. Of course, when you burn biomass, you emit CO2 to the atmosphere at the point of combustion. But the key difference between bioenergy and fossil fuels is that bioenergy operates within the short-term carbon cycle, whereas fossil energy systems transfer carbon where it was stored safely underground into the atmosphere, where it essentially causes permanent warming. So this means if we want to quantify the climate effects of any particular bioenergy system, we shouldn't be asking, how will power plant emissions change if we burn biomass rather than coal? Instead, we should be asking, how will greenhouse gas concentrations in the atmosphere change if we modify our agriculture and forestry systems to supply biomass for energy and other bio-based products, such as wood products that can displace concrete, steel, and plastics and aluminium? The answer depends on many factors related to the specific features of different bioenergy systems, and that is the focus of my talk. For a start, we can get the biomass for bioenergy from many different sources. The types of feedstocks we can find come from waste, such as from construction and demolition, urban green waste, and food waste. And here we can think of bioenergy as a waste disposal measure. Then there are crop and forestry residues and manure from livestock production that can be used and seen as a co-product of food and soil log production. Then there are dedicated energy crops, such as short rotation coppers. And each of these different feedstocks has different properties in terms of its use for bioenergy. Amongst the different production systems that we could use for dedicated energy crops, the yields are going to vary per hectare, depending on the location, the climate, and the soil type, and also the type of production system. This figure is just illustrating for a range of different forestry species harvested in Australia, that depending on the species, you get a different proportion of the stem that ends up in the soil log, and therefore a different proportion that ends up in the harvest residues. So depending on the species, you can have a different amount of harvest residues produced per hectare that could be available for bioenergy. Then there are a wide range of bioenergy technologies and products that can be produced. I'm sure you're familiar with the technologies: combustion, pyrolysis, fermentation, transesterification, anaerobic digestion, and the products that can be produced: heat, electricity, liquid fuels, and biogas. And bioenergy plants range in size, from cook stoves through to plants that process tons of biomass per hour. And each of these options has different inputs, different conversion efficiencies, and different co-products. So not surprisingly, they have different emissions per megajoule of energy product. Generally speaking, the emissions savings per unit of feedstock are highest for heat applications and for combined heat and power, then electricity, and lower for biofuels from lignocellulosic biomass. We have to consider the emissions along the supply chain, and they are going to vary depending on the type of production system, the processing technology, and the transport distances involved and methods of transport. We also need to think about the co-products from our production systems. Forest biomass for bioenergy is commonly produced as a co-product of timber production. And timber products obviously store carbon, and they can reduce emissions by displacing more greenhouse gas intensive building products, as I mentioned earlier, like concrete, steel, and aluminium. A range of studies that have looked into that substitution value have identified that the emissions reduction is around 1 to as much as 3 tonnes of carbon per tonne of carbon in a functionally equivalent wood product. And it's particularly high when you look at wood-based textiles, for example. Another bioenergy system where co-products is important is pyrolysis. Pyrolysis involves heating biomass in a low oxygen environment, and it produces a combustible gas. It can produce bio-oil, but it also produces a charcoal-like material that we call biochar that can be used as a soil amendment. Now, biochar has very stable carbon that lasts for hundreds to thousands of years when it's incorporated in the soil. So pyrolysis is a bioenergy option that leads to carbon dioxide removal or negative emissions. Biochars also have a range of other climate benefits, such as reducing nitrous oxide emissions from soil, nitrous oxide being a very powerful greenhouse gas. And also it can offer benefits in terms of increased water and nutrient retention, and can improve crop yields by, on average, 10 to 42% in the meta-analyses that have been published. And we've already heard from Andy and Sabina about the option of BECCS, bioenergy linked to carbon capture and storage. So here's an option where the fate of the CO2 matters, and we can have negative emissions if we capture the CO2 and store it geologically. But when we're trying to quantify the climate effects of a particular bioenergy system, there are a range of things we need to consider in terms of what would happen if we didn't have this bioenergy system. In other words, what is the reference system? One important aspect is what is the energy source that you displace with your bioenergy? I'm sure you're all familiar with the fact that coal emissions are very high. The greenhouse gas intensity of electricity produced from coal, which unfortunately there's a lot of in Australia, is very high. This is just illustrating the temperature effect of a pulse emission, the same amount of energy produced from different sources. In the dotted line is the coal, the solid black line is natural gas, and the grey lines are bioenergy, showing that if you're displacing coal, you're obviously going to get a greater climate effect. By the way, the bioenergy goes down over time as the forest takes up CO2. Another important issue is what would happen with the land. What is the reference land use? Now, if you have an existing forest that's managed for timber production, then it's likely that if you don't harvest the residues for bioenergy, you'll continue to need the forest for timber. So the appropriate reference there would be ongoing harvest for timber and perhaps leaving the residues to decompose in the forest. Some people are talking about foregone sequestration, I think, in the chat. And this is the issue when a reference that is used that is a no harvest residue. That is an assumption that if you didn't harvest biomass for bioenergy, the forest would remain unharvested. So that is sometimes a relevant reference. It really depends on what is the most likely use of the forest if you didn't have a bioenergy incentive. When it comes to energy crops, they might be displacing agriculture. They might be displacing food production and could lead to indirect land use change. On the other hand, they could be planted on marginal land that's very unproductive, that isn't producing a lot of food, and that can actually be beneficial in terms of arresting land degradation, for example. This graph is a very simplistic, stylized example of what Florian was showing in his assessments of the different countries in the Boreal region. The top graph shows a single forest stand, and at the bottom, an idealized forest estate in which there's equal areas of each age class. So an equal area of forest is harvested each year. And that means that the carbon stocks across the landscape will remain constant, at least theoretically. So the blue line is the business as usual. And if we extract biomass for energy, that could lead to a reduction in the average carbon stocks shown in the red line. And that would be a carbon cost of bioenergy. But it could instead stimulate investment in improved forest management, which could lead to increased growth rate, which could eliminate the carbon cost or even enhance carbon stocks, as shown in the green. And that's in fact what Florian has shown for Finland and Sweden, where they have intensified forest management and at the same time extracted more biomass from the forests. Now, incentives for bioenergy could lead to expansion of production forestry and increase the carbon stocks at a regional level. Energy crops and biomass production can be integrated with agriculture and forestry land uses, and that can minimise the risk of displacement of food production. And it can give synergies such as reduced erosion and shelter for crops and livestock. But as Andy mentioned, the integrated assessment models that are used to develop the scenarios that inform the IPCC reports, the scenarios that Andy showed, are not so sophisticated when they model biomass production. Understandably, when you're trying to model the whole world, it's not easy to be nuanced. And so I would suggest that these type of integrated production systems could be deployed, and that would reduce the amount of land that would be required to produce biomass for bioenergy in order to generate the negative emissions that the IPCC report identified would be required. The third aspect of the reference system that influences the climate effect is the fate of the biomass if it wasn't used for bioenergy. Oops, there we go. Forestry residues could decompose slowly on the forest floor and continue to store carbon, especially in cold climates. But on the other hand, they are sometimes burned on site, for example, to manage fire. That's what happens in Australia. We're returning the carbon to the atmosphere immediately. Processing residues are sometimes burnt to waste, or they could alternatively be used for composite wood products. So if you diverted them for use for bioenergy, that might reduce availability for another purpose. And then we need to think what happens to the end-of-life wood products. If they are landfilled, they actually decompose very slowly in that anaerobic environment. And indeed, burial of logs is now recognised as a carbon dioxide removal strategy in some schemes, which I find a little strange myself. I've mentioned all the elements that you need to know about in order to quantify the effects of bioenergy on the climate, but it's actually often difficult to track down the biomass flows and their alternative fates because bioenergy systems are often complex, as illustrated here in an example of Swedish forestry, which shows that bioenergy is produced at several stages along the supply chain, and that much of this bioenergy is in fact used internally within the wood products sector for processing. If you put together all the information about the elements I've mentioned, you can quantify the climate effects of a scenario that includes bioenergy and compare it with another that excludes bioenergy. So this is an example of a study in New South Wales native forests, where we contrasted the climate effects of continuing to harvest forests and then using the residues for bioenergy versus a no harvest scenario. The no harvest is shown in the black line. What we found was that when you consider the carbon in the forest in green, plus the carbon in the products in service and in landfill in light blue, and the displacement benefits of bioenergy in the orange, and the substitution benefits of wood products in the yellow, the managed forest scenario gives a greater mitigation benefit in the longer term. But there is a period in the interim, in the short term, where the conservation forest looks advantageous from a climate perspective. Now, finally, one element that is often overlooked when we look at the climate effects of a bioenergy system, when we're looking, I guess, at the local scale, is the effects of bioenergy on energy system decarbonisation more broadly. Because bioenergy is storable and dispatchable, it can play a strategic role in stabilising the grid, allowing more rapid expansion of the intermittent renewables. And this is a study that showed that, also from Australia. It showed how bioenergy in the green can fill the gaps when the solar and wind resources are low, especially in winter. And this decreased the greenhouse gas intensity of the grid and reduced the cost of electricity because it reduced the total installed capacity required. It's also interesting, finally, to consider the effect of bioenergy on the global carbon budget. Now, please remember that the size of the carbon budget, that is the amount of CO2 we can put into the atmosphere before exceeding a certain temperature, is uncertain and influenced by many factors. But we are rapidly expending it on fossil fuel emissions, and we need to spend it on fossil fuel emissions associated with deployment of mitigation strategies, such as solar farms and electric vehicle infrastructure. We're happy to do that. We could choose to spend some of it on establishing sustainable bioenergy systems by mobilising more forest biomass, for example, that could reduce, it could occupy part of the carbon budget. But on the other hand, as illustrated in Florian's examples, some bioenergy options or incentives for reforestation and management, or more intensive management of forests, could even serve to expand the carbon budget. So I just want to finish with a quick recap. The climate effects of bioenergy depend on a wide range of context-specific factors. The biomass feedstock, whether it's residues or purpose-grown energy crops, its properties, and it depends also on the location, the type of technology and the scale at which it's applied, which influence the efficiency and the fossil fuel and energy inputs required, the effects on land carbon stock, including the possibility of indirect land use change, and the often overlooked aspects of indirect effects on incentives for investment in forest management and reforestation, which will affect the wider energy system and the construction sector as well. What we find is the greatest climate benefits are achieved when biomass is obtained from residues and from energy crops that are integrated with agriculture and forestry, when there is an efficient conversion process to produce the products, when greenhouse gas intensive fuels are displaced, and when the co-products are used also to displace greenhouse gas intensive products. When bioenergy demand leads to increased forest carbon through incentives for forest management, as we discussed, and when bioenergy supports energy system decarbonisation and implementation of the bioeconomy. And finally, if the CO2 is captured and stored durably, geologically, or in long-term products, that will obviously enhance the impacts in terms of climate benefits from bioenergy. And thank you very much for listening. If you would like more information, please contact myself or Jan Bountes. Thanks, Jim.
Thank you very much. So there are many questions, but I'll ask you just one. How is it that, why is it that so many studies related to biomass can have very, very different results?
Thank you, Jim. Yes, if you're familiar with the literature, you will have seen that there are a wide range of views in terms of the climate effects of bioenergy. And partly this is because bioenergy systems differ inherently, as I described, but it's also partly due to the fact that different studies use different methods. And some of the studies use a much more narrow system boundary than others. I explained the importance of looking at the effects, not just from the smokestack, the emissions to the atmosphere from the combustion site, but also looking at the effects on the energy system, on the building products sector, on the land carbon stock, and more indirect effects that come from the market-based effects and policy incentives. So this is one of the key reasons, the system boundary that affects the results. There are other elements which are important, which are the assumptions, the assumption of the reference energy system or the reference land use system, as I discussed. They have a big impact on the results as well. I think that's probably enough on that point for now. Thanks, Jim.
Thank you. Very difficult to harmonize all those factors.
Yeah.
Okay, we have our third and final poll that will be pulled up. We'd ask you to select three choices, and then it's my pleasure to turn over the chairing to Paulo Franco. I'm going to step off and let Paulo take over and bring up the results of the poll when it's done.
So, Luc or Jim? Yes, exactly. Here we are seeing the first results. It's my pleasure to step in. And we see they're still changing a bit, but the first is a carbon tax and tax on fossil fuels so basically the polluter pays principle. And then the second one, there is reduced investment risk for early market players. And then very close to each other, other options like obligations or more funding for research, innovation, and technology. Now, first of all, many thanks to all the speakers. These were great presentations, a lot of materials, which could open an endless panel discussion. We will try to focus that. I now really rely on Luc to help me in collecting some of the questions from the Q&A. Luc, are you connected?
Yes, I'm connected. Can you hear me?
Yes, I can.
Okay,
so
great.
What would you like to extract as a first question from the audience that I can then redirect to the panelists? Or otherwise, of course, I can step in with some.
All right, yeah. There's several questions from the audience. Of course, we also have the central question, which is related to our last poll,
Sure.
which is on what is needed for deployment. But maybe a first one, there was some comments also from people in Africa saying, well, we have a different situation in many of the regions that we have difficult access to energy. We have a lack of capacity also to do something with the biomass. Stop my video. Some lack of capacity to do something with the biomass, and people from the West are asking us to conserve our forestry, our forest systems. So how to deal with this? So I don't know if anyone of the panel or the speakers has an answer to that. So how getting the balance right between sustainable forest management and seizing the opportunities of modern bioenergy in these regions?
That's an interesting one, which could have actually some more questions. Who want to give a first go to this one? Anybody? No volunteers? Annette, please.
Of course, this is not a problem that has an easy answer. But some of the options include introduction of more efficient uses of the biomass, more efficient cook stoves, more efficient energy conversion processes, and also the introduction of reforestation, specifically wood fuel plantations. And I know this is easier said than done, but these are two small suggestions that I would make. I'm hoping that Sabina has something useful to offer.
Yes, maybe I would actually, it was already a very sophisticated answer in that, but I would probably also add that if you translate from what you see in terms of scaling from the scenarios to the context of your country and so on, that might actually always seem like a big discrepancy and a huge challenge. But I actually strongly believe that we will see also not only over technologies, but also and practices, but also across geographies, a diversification, a diversified portfolio. So not necessarily having the types of technologies that we already talked about scaled, but also the kind of things that Annette was talking about. And that's why I emphasized so much that I think we need to bring together the scenarios where you have these very aggregated, where you have this very aggregated view together with what actually works in this context. And maybe maybe it's not for some of the large-scale bioenergy technologies that you currently see in IAMs in the context of your country. Maybe it's something else, but I think it's good to keep an eye open for things that are not currently in the models as well, in order to also live up to other policy goals, specifically Sustainable Development Goals.
I see Florian with raised hands. Florian, please go. But then I have another question to Annette, still on this.
Yeah, just to chip in also 2 or 3 cents here. I think from a technology point of view, everything is on the plate. The question is now how, and similarly to my 4 speakers also, how to implement that accompanied with the right policies. And if the one who asked the question says, how do you keep us away from our forest resources just in order to protect it? I think this is not our intention. And I think also from what I know from IEA Bioenergy, they have a lot of experts around there who are developing these best practice studies, etc., to see what is working really in which place and what not. And we don't keep people out of the forest, but I think personally that one can do both at the same time, as the presentations have shown, that we can provide the necessary resources. We cannot provide it for all and everywhere all over the world just from biomass, but we can provide in these particular areas enough resources while still protecting the necessary biodiversity, etc., to keep the ecosystems up and living. So I think we have to take these best practice examples, and we have to combine it with much more bottom-up research, including, and this is most important, the local experts and scientists who can contribute here tremendously from my point of view.
Andy, I see I see a message from Andy, for whom I think this is 3 a.m. in the morning. Andy, do you want to say a last thing? Yes, exactly. That is still your eyes are open. Would you like to give a comment on this question or anything else that you would like to say before getting to your very well-deserved sleep?
I may just wanted to say thanks for the chance to contribute, and my fellow panelists are much better placed to answer technical and detailed questions. Maybe just sort of on the overall issue of how do we deploy our energy in different parts of the country. I just want to also recognize that one of the findings from the Working Group 3 report is, of course, the critical role of climate finance and the especially the large gap in finance in the agriculture and forestry sector. And so without finance support through redirecting investment flows and through providing additional climate finance, we cannot meet those challenges as well. It's not the sole solution. It's a complex problem, relies on capacity building, influencing local systems, but it's also an important component overall for addressing climate change. And it's important to recognize, I think. But thanks, I'll try and listen for a few more minutes, but I'm afraid I have to try and catch up on some sleep before my day begins.
No, of course, we totally understand. I thank you very much for your excellent presentation, and also I think for showing some of the critical points that I would like to slowly discuss in this panel discussion. One for me is the importance of the metrics of land use, which is used in different ways depending on where you are and who you are to criticize or not to criticize. And I think your points about scale and land use is something that I would like to come back during this panel discussion in the next half an hour. But before we do that, Annette, coming from LCA world, you correctly say the crucial point is to choose the right reference system. Now, in Africa, we know roughly, we know in general, or let's say anecdotally, what are the very bad impacts of the traditional use of biomass for health, But do we have a good reference system for the impact of the traditional use of biomass in Africa? Do we know how to estimate what would be the benefits in substituting this with better technologies and actually to give the right response to the question, what happens if you take us away our biomass? Well, that's not the real question. Do we have this reference system assessment?
Unfortunately, our figures are very rubbery for unsustainable fuel wood use, especially in Africa. The challenge is enormous. Clearly, we're talking about many people involved in supply chains in a situation where there isn't good data collection and it's not easy to gather the data. And so that is the situation, that we do not know in detail with accuracy how much fuel wood is used in this way. What we do know is for individual systems, what the efficiencies are. We have information about the decline in carbon stock in many of these countries. We have good ways of estimating that now, of quantifying that. Attributing it to biofuels versus other uses of wood products, forest products, is of course difficult. But we do have studies comparing different ways of improving the efficiency for smallholder production systems, ways of improving charcoal production, for example, to minimize the emissions associated with charcoal production, studies on improved cook stoves, pyrolysis stoves, for example, that allow you to cook dinner on a handful of leaves and grass rather than having to have solid wood, so you don't need to be going to the forest in order to bring back wood, and certainly reduce the amount of wood required. So it's a challenge, but we do know some things about it, and we need more information before we can have, I guess, a better outcome in terms of managing this issue.
Thank you so much. I would just like to remind that roughly 40% of total biomass consumption, we estimate, is coming from traditional uses today. And fixing this in this decade would open a big potential for the expansion of other more sustainable bioenergy and biomass in general uses for bioproducts and other things. Luke, again to you for the Q&A selections.
Okay, there's a few questions which have to do with the intensive sustainable forest management, mainly to Florian then also. So is two sides of it. One, are the advantages solely related to a lower fire risk? So that's one thing. And the other question, how important is this role of sustainable management in tropical forest areas? Do you have an idea of it? Because now it was mostly to boreal areas, but do you have an idea about tropicals?
Okay, well, let me try. First, is the advantage only due to fire avoidance? No, obviously. The fire comes in addition and makes things worse in places where it's already very bad. A good forest management is the basis. On the other hand, we see also that we move towards younger forest stands, which means that we are sequestering simply more carbon because younger trees are more productive. And if the trees become older, the productivity gets less until they actually emit more than they sequester. So this comes, of course, also from management. This is, of course, only looking now only at climate mitigation objective. If we here look into biodiversity objectives, which we should do in addition and always, then we can, so to say, add some more, or there is room for improvement. Let's put it like this, because the systems in the Nordic countries are known as very intensive, very production-oriented systems. very single species oriented systems. But if we see how much carbon is actually accumulated in addition to the harvested part, then we can have the luxury, so to say, to dedicate some of that also to biodiversity, and we still would be well off with doing such sustainable forest management. I don't know if I answered that question now, but there are many factors that play together. I think also that tree species composition is a big thing here to be considered if we only deal with one type, which is called spruce, and there is sprucification in addition, which means more and more spruce is favored also by a large population of deer and moose, etc., in these areas. So everything comes together. If we move to the tropics, the system is of course much more complex because we are not dealing with a single tree species forest here, and forest management in the tropics is varying substantially to the boreal countries. What we know is that, for instance, we can have different types of restoration in the forests, in the tropical forests applied. And here again, it depends very much whether we are looking or what's our objectives. Are we purely looking for mitigation? Are we looking for re-establishing what has been there before after a wildland fire or several wildland fires? Or do we aim at a combination of these and trying to provide income to small-scale farmers, for instance, who need to send the children to school, very bluntly said. And here we have to find the right solutions. Also, in many cases, it is a combination of land use that is not optimal combined with cattle breeding. The problem here is that after slash and burn methodology, so to say, cattle is put in here. After 2-3 years of grazing, the soil is completely depleted and there is no nutrients left over. And we have a problem in restoration. And of course, the little thing that grows might then become victim of fire again. So from my point of view, important thing is, and also in order to use the very strong recovery potential of tropical areas, to keep cattle out of burned or harvested areas, and half of the problem is solved with that. But of course, this is a little bit naive with respect to how land use in reality happens. But this is one of the management options that I would wish to see here. Like we have to keep the deer rate in our areas, temperate and Nordic forests, low in order to allow other trees than spruce to survive. We need to control and imply better land use regulations, particularly with respect to cattle and grazing in the tropics.
Okay, thank you.
Thank you so much. Luke, you have the whole control of the huge list of questions. At some point, we need to converge also on the policy measures, because this is, all, of course, one important part of discussion.
Okay. There's one thing maybe coming back also to the CDR issue, and that afforestation and treating forest also as a way to store carbon, and also to how to recognize and count that. You think there's an issue? A lot of it depends also on modeling, on what's going to happen in future with these forests. Do you have an idea of where are the risks, and is it a good way to rely on these long-term models, or how exactly do you think these things should be quantified? So the carbon removal actually from forestry. I think Sabine, it's a bit directed to you, but maybe also others.
Can you repeat the last one? I had a short outage here.
Is it right to rely on long-term models to kind of monitor or to quantify carbon removal from forests? So if we count on carbon removals as kind of an offset of fossil emissions, how can we rely on that, and how can models play in there?
Yes, I do think models should actually be used for what they're designed to use, namely to explore different futures. And in that sense, I think they are useful. But I did see also in the Q&A that I was also just trying to keep a little bit afloat of, that there's a lot of criticism of models and how you can actually use them to base actual policies on that if we're already having this discussion how much they're missing. And that's also true, right? I mean, if you compare actually with what you get from inventories, and then you look at the bookkeeping models that then of course feed also into what we see then from the typical IEM pathways that Andy has been showing, and also I and others, then you see, of course, especially when it comes to the land use emissions, quite a big discrepancy, right? And I mean, other colleagues are of course more expert in that. Giacomo Grassi has published on this and so on. And I think this is something to make transparent and to keep very much on everybody's radar when policies are formulated, because that will eventually mean, of course, that if we base our policy solely on the modeled pathways, that we might actually be having a gap that we still need to cover with additional removals. So that's something to keep in mind when using models, but I do think they have their benefit in exploring what sort of changes in the system when you sort of pull certain triggers. And for that, I would actually not like to dispense with them, but just make the caveats, make people aware of the caveats that we need to apply when we use them to base policies on there.
Okay, thanks. Maybe Annette, you can also say something about this, because I know that models are also applied in reference systems of what would happen with the forest. Sure. So
yeah, yes, you're alluding to the fact that it's very hard to know what will happen in the counterfactual situation. Yeah. And so this is another uncertainty when we do these calculations. But I would agree with Sabina, we're better off with models than without anything to guide us. And of course, if you're trying to model the whole world, you can't model it in a very sophisticated fashion. But the models are improving. The people who develop the models are doing their best to introduce the other carbon dioxide removal methods that we mentioned are currently missing from the integrated assessment models. So I expect that the models will become more and more useful and more accurate over time.
Okay, thank you. Yeah, I see a conclusion here. All the models are wrong, but some are useful.
Okay, that's.
But it depends a little bit on what they take them for, right? Yeah. Scenarios are for exploring certain decision spaces, but I think they're not meant to predict where we actually will land.
Can I ask, in the meantime, while Luke looks for other things, a round of question on carbon pricing? And the reason why I'm asking this, I think you mentioned, everybody mentions carbon pricing always. Sabine, in your presentation, I think you mentioned it several times. I have two slightly provocative questions. First, if you apply carbon pricing, is it one level of carbon pricing, or is it sector dependent or dependent on the uses? In economic theory, it would be one to be an optimal solution, but then reality is very different. And number two, in particular for biomass, what is questioned by the criticizers is the capability of biomass to reduce the carbon emissions. So if you don't, so there are two reasons why the carbon pricing is not necessarily the easiest thing to apply in the case of biomass. I'm deliberately a bit extreme in my question. Who doesn't want to comment? Who does want to comment?
Maybe I can start off because I was tasked with the regulatory aspects in this panel. So first of all, carbon pricing, I do believe it's an effective way to do climate change mitigation, to actually price the externality that's currently not priced. So basically making people pay for what they impose on others. That's basic economic theory, and I think that makes a lot of sense. Now, how that will look like in practice may look differently, and I already pointed to a couple of issues why you would want to differentiate prices as well, right? You might want to differentiate price. You might want to have different prices because you want to separate targets, right? You don't want cheap credits to undermine more expensive mitigation options to be pulled. So that's why you might want to have different markets. In theory, you could also put it all in the same market, and then every ton that's still around when we want to hit net zero would have to sort of pay for its own removal, so to say, and the market would then pick the winner. That's the theory. That doesn't deal, of course, with the question of what happens when you go net negative, right? You need another revenue stream then in order to finance that. Another thing that I mentioned was heterogeneity when it comes to permanence. Some of the land-based options might not be as permanent as geological storage, or you might have these risks of reversibility that Florian pointed to. So you might want to discount for that when you use a pricing scheme for carbon. So there are all sorts, or you might actually want to pay a premium if you think, oh, this is actually something that the current market doesn't give us yet in terms of CO2 price, but we really can benefit here from being an innovator, from benefiting from innovation spillovers and making some headway on the learning curve. So then you might want to put a premium on carbon prices. Or you might actually want to price in other externalities in as far as you can measure those. I mean, we're already arguing about carbon, but then measuring biodiversity is yet another issue. So there are all sorts of reasons why you might want to differentiate carbon prices, and that lead you to deviate from theory. And the second element was that bioenergy biomass might actually not be carbon neutral. Well, that actually,
just to be clear, in this audience, everybody is
yes. I don't think I need to convince anybody.
Yeah, but as you know, this is very controversial.
But maybe to give some further ammunition here from an economics side, if you would comprehensively price carbon and then also cover the land sector, right? Then you would basically also address issues of leakage into other sectors. So that also sort of argues for comprehensive carbon pricing in order to make sure that that you don't leak into sectors that are not covered by that. So it's also a little bit my duty as an economist to come up with a bit of a defense for carbon pricing, I feel, but Annette will say more in defense of bioenergy then.
Annette wants to intervene.
Yes, thank you. Sabina gave an excellent and comprehensive answer, but there was just one point that she made that I want to emphasize, and that's the one about perhaps differentiating on the basis of co-benefits, because I'm actually frankly a little concerned that the world seems to have swung from enthusiasm for nature-based solutions now to enthusiasm for permanent solutions. So this is creating an incentive for people to demand DAX credits and to be less enthusiastic, as I say, about reforestation, soil carbon management, and integrated biomass production for bioenergy and for biochar and for BECCS. And I think this is really unfortunate because there are so many benefits that can be obtained from these land-based options. And I think it would be a real shame if we were too concerned about this issue of the risk of reversal and didn't recognise these potential co-benefits and create systems for our carbon pricing that actually take this into consideration. Of course, land-based carbon pricing has been around for a while, all associated with reforestation, and now we have some schemes that recognise soil carbon management, and these schemes have put in place measures to manage the risk of reversal, the fact that this carbon is vulnerable, and so we don't have to leave it out of our schemes just because of this fact. Thank you.
Yes, I would agree with Annette, and it's not only the co-benefits, but also I think it's a little bit drastic to say, I mean, what some people are actually suggesting, that we should only account for the really permanent stuff where things are removed for like 100 or even 1,000 years, because I mean, any time that we can buy in the face of where we are is actually valuable.
Absolutely. and I think, please, Florian.
Yeah, just to mention one more thing. So, and to see also the let's say the positive side of more permanent or technical CDR solutions. I think nothing works without land. And if you have in mind, we just, for instance, try to produce sufficient aviation e-fuel from direct air capture. What that needs in terms of still, renewable energy supplies and water supplies, etc. All this needs to be provided and managed in the right way. So in the end, there might be a quite healthy mixture of land-based and nature-based and nature-climate solutions and land-based CDR and technology-based CDR options. So I think we don't have to worry here too much, but of course, yes, we are here to promote bioenergy, and here the nature climate solutions are in principle much closer. Yeah, that's clear.
Can I, while Luc, do you have another direct question? Otherwise, I have one.
Please go ahead. Go ahead.
Because Florian, you mentioned a keyword for me, which is land. Can I ask the naive question? Why do you think that governments do not look enough at land use governance and land use planning? Of course, there are multiple reasons, but in your experience, why this is not much more prominent in the policy making?
Well, I mean, first of all, I think it's a difference whether we look into the developed world and the not so much developed areas. I think that resources, and they are all land-based, and the one natural resources, they are all land-based. They are kind of what is always there and what gets protected if economy in principle runs very nicely and smoothly, and once there is a little hiccup, as we are facing again presently, these resources are to be drafted again without any regulations to be followed. I think this is a big danger, and this is, of course, this reaction, which I feel is quicker in developing countries than in let's say the northern hemisphere, but that's also not true. But yeah, in developed countries. So this is a bit of a problem that regulations can change or can be changed too fast in political cycles, and I think here we are nowhere better off, but they seem to be a little bit more stable in developed countries. So this means that we need to invest here massively in some of the SDGs, capacity building, women power, etc. I think here there's still a lot of room for improvement. These are my first guesses, that there's too much changing politics, not policy necessarily behind it.
Annette wants to intervene.
Yes, I just wanted to mention that funding to implement integrated landscape management approaches is a big priority under the Global Environment Facility. There's widespread recognition of the need to tackle the various environmental objectives simultaneously and the broader range of the SDGs. And one of the initiatives in particular in this regard is land degradation neutrality, which was promoted by the UNCCD, but it is SDG 15.3 as well. And the idea there is that in order to manage land degradation, you need to take a land use planning approach and anticipate the impacts of your current land uses and intentionally reverse land degradation, rehabilitate or restore degraded land in order to make up for land that is becoming degraded by your current land uses. And we've identified biomass production for bioenergy as one of the particularly useful land uses that could be applied for land rehabilitation to support the achievement of land degradation neutrality, but that it all depends on effective land use planning that's inclusive and takes into consideration the wide range of environmental objectives and other human objectives, of course.
Thank you. Any other comments? I mean, from our perspective, we think that a better land use planning is really key for going forwards and to convince policymakers of the advantage of biomass and of nature-based solutions, because otherwise it's very difficult to make this discussion somehow. Luke, do we have anything else from the Q&A?
Maybe one thing I derive here also is, well, the matter of land use it's not just a choice between energy crops and doing something else with it. So there's usually also multiple things coming out. There's also what's popping up more also is intermediate crops and cover crops. Do you know, well, I know Andy is not here, but has this also been integrated in the global assessments of land use? That there are options to not negatively impact the food production, but doing something in excess?
Please, Annette.
I'm hoping that Sabina and Florian can help me here too, but as far as I'm aware, the land use options for such as cover crops to increase soil carbon are not modelled in the integrated assessment models. And the evidence for cover crops is actually quite inconclusive in different land use systems. And so this is one of the types of practices which could be effective in some locations, but certainly not all, and is not yet integrated into the integrated assessment models. So I'm hoping Sabina can expand on that.
Yes, maybe just to complement. So integrated assessment models have become better at integrating some of these things that also pertain to the land use sector and especially agriculture, in as far as they have been coupling to large scale, spatially explicit and quite detailed land use models that are again coupled to a whole suite of biophysical models. So that sort of opens the door to kind of cover these kind of things. But as Annette also rightly said, they're still, of course, dependent also on the kind of empirical evidence going in there to be conclusive in a sense. So I think this is something that we will see. Modelers will try to capture more, but I think, yeah, we're definitely not there yet, and definitely not in the model intercomparison exercises that we typically refer to when we look at these whole spaghetti graphs to get a good sense of how the scenario spectrum looks like. But since I think Florian is leading actually a group looking at this type of modeling, I hope that he can complete the picture.
Florian, please. You're muted.
Oh, better to unmute, you're right. So just a few words also to complement here. So I don't know if people are very familiar how, for instance, the land use part of these integrated assessment models work. In principle, we start the whole thing at very detailed process or biophysical models that provide a lot of information, very detailed, as I said, and provide these then to, and in our case at IASA, to a larger economic land use model, and the economic land use model then links up with the energy or direct IEM model. And a lot of information is presently still lost in this linkage between the biophysical modeling and the economic land use modeling, which we are working on, of course, and in every round there is more detailed information put forward into the IEMs. However, these perennial or intermediate cropping systems, which are so important, are not yet in there. Our biophysical models, and this is what Sabine mentioned, I'm responsible for, we can of course mimic that already perfectly, but it is limited in the resolution of the next higher level model. And this is our focus now in order to improve these linkages and really bring in all the nitty-gritty information as much as possible forward, and aim at having improved IEMs. This has drastically changed over the last 2 IPCC cycles, I would say, where we see that there is a lot of improvement, but again, there is not everything now still put forward, and it will probably still take another 1 or 2 cycles in order to come up with IEMs that pick up also the nitty-gritty information and better combine this bottom-up and top-down information that are then in the end processed in the IEMs.
Thank you so much. Luke, if I may read the last question that came in, because I had the same question for me. And actually, more in general, is how the bioenergy community can respond to the pressure which is coming outside. This Q&A says, how can the bioenergy community respond to the call for urgent removals on timescales of a decade or 2? This implies removals now are of greater climate value than those after 2050. This is sparked by your graph, Annette, showing that the harvesting forests only exceeding the unharvested forest in, where was it, in Australia, I think, in 50+ years from now. So this is obviously a good provocative question. Do we have this time?
Okay, well, I will start. What my graph showed was that if you stopped harvesting the forest, you obviously will have an immediate increase in the forest carbon stock that continues to increase for some time. And so it shows a period where apparently the no harvest scenario is preferable to the ongoing harvest and use for wood products and bioenergy. But when we get to 50 years' time, when we still need to manage climate change, unfortunately, it flips, and the bioenergy option is much better than the harvested and than the unharvested option. And that study also left out the likely increased risk of that carbon that Florian highlighted, because an unharvested forest is going to be at risk of loss of the biomass due to, in particular in Australia, wildfire. What I think the bioenergy community needs to do is to help people to understand bioenergy from the perspective of the system perspective, because to me the real issues are that people are looking far too narrowly. For example, comparing the emissions from a pile of wood chips to a pile of coal and finding that there's more emissions or the same emissions from coal, from wood chips as there are from coal. But that's because they're not considering the bigger picture, the fact that the biomass came from a biomass production system that took CO2 out of the atmosphere in the first place. Clearly, we do need to also reassure the community in terms of forest policy and certification schemes to ensure that the biomass that we use for bioenergy is extracted from systems that can demonstrate sustainable biomass production, and that other issues such as biodiversity are being taken care of. I'm sure others have plenty to add to that. Thanks, Pamela.
So if I can reply deliberately in a provocative way, and I put myself in the shoes of, the aggressive NGOs, I'm partly convinced by your answer because they would say we need to mitigate right now, the most that we can, so we don't have this time. Now let me expand my provocative mood 1 second. And apologies, I really do it deliberately. It is not for this community. The problem is outside. The criticizers of bioenergy use very simple language. Oh, this is bad because the payback time of CO2 is too long. They don't make any distinction. And then you come today with a wonderful set of very detailed modeling. Annette, you come with a very good list of it depends, but in this oversimplified communication-based world, this is not enough. Now, the reason why, where I'm trying to converge, in the very, very short term, notwithstanding the longer term implications of a better, how managed forests, how can we convince the criticizers that managed land use resources are better than just abandoned one or not managed, be it forest, be it other feedstocks? Maybe we should separate better our discussion per region, per feedstock, rather than speaking about bioenergy in general. Sabina, I take one of your graphs where you were speaking about land-based leakage, and you said a very simple thing. In the short run, focus on measures that do not increase demand for land. Full stop. And now I'm trying to get, for this last few minutes, in the short term, what is, in your opinion, the main priorities that needs to be presented to policymakers to really raise the profile of biomass, of bioenergy, of nature-based solutions, and avoid this risky trend that someone of you mentioned, that now suddenly everybody is fan of DAX or only technology solutions. Sorry for being long in my question, but I would like to converge in this direction.
Yes, I mean, the message that I wanted to send with this is that, I mean, we're not getting any further by sort of addressing the concerns that are put on the table and that you just mentioned as kind of like shorthand communication as well. By just ignoring them or just like putting them off. I mean, I think we sort of need to engage in the debate and we because otherwise the debate will forestall forever, and that's also not really in the interest of raising the profile of bioenergy. But the message I wanted to send is that we actually have ideas, we have approaches how to address the kind of concerns that are being put forward, policy instruments that could be integrated into the climate change mitigation policy architecture if bioenergy was to be covered by the same type of instrument, for instance. And while we're sort of setting up for this, right, improving our capacities for MRV, improving the way that additionality is ensured, and so on and so on, and that also sort of cross-border trades and co-benefits and trade-offs in other policy areas are taken into account. I think there's actually no time to lose, and it may make sense to sort of then in the short term focus on land saving policies, and that could, for instance, be more efficient biomass, right? I mean, Annette was saying we could grow on marginal land and so on, but it could also be a combination with the kind of things that Andy was mentioning, right? Improving on the demand side, and for instance, in terms of diets, using much less land for the kind of things that we're currently doing, and thereby freeing up more land for other purposes. So I think while we're evolving to be able to cover or to address the biomass scaling challenges that are currently on the table, there's a lot of other things that we can do to sort of contain the kind of risks that people perceive. So yeah, but I think we sort of have to do something about it in order to keep the debate going, because I agree with Annette that it's not very productive to pin the geological storage site against the natural storage site. And I think scientists are partially to blame for this, right? We've maybe also not offered good language for this debate, right? Sort of pinning natural climate solutions against technological ones, and then half of what we're talking about, like BECCS, doesn't even fit in there, so it's kind of weird hybrid options. So a good taxonomy would also actually be a good start. A more differentiated taxonomy would give you a good start to deal with that. And Working Group 3 has made a nice sort of push into that direction already.
Annette or Florian, do you want to intervene? Yes, Annette wants to respond.
I have a quick one. I think promoting the kind of results that I showed from the study that showed if you have some biomass in the mix, you need less solar and wind. Everybody loves solar and wind, but surely they understand that we can't have it tomorrow. So if you can use some biomass to help you get over the hump and to avoid the need to continue using fossil fuels, or especially to avoid the need to develop new fossil fuel infrastructure, then that is a really useful contribution that bioenergy can make to decarbonisation of the energy system.
Florian, please. I have a reaction to this, but Florian, please go ahead.
Just very shortly, I think with whatever we do in the short run, we have to put an eye on the long run. Because particularly, and I can only speak for the Northern Hemisphere forestry here, we have to, in principle, look forward in terms of 50 by 100 years. If we now want to plant more fire-resilient tree species, then this has to happen in order to avoid huge losses in the future by 2050 or 2100, what I have shown so far. And also, if we would like to identify areas for afforestation where the additionality accounts, then we need to give at least 10 to 20 years in order to get this going. So immediate is almost nothing unless the things we are doing. And part of what we are doing is bioenergy from my point of view, at least in Europe or in the Nordic countries, very much sustainable way. This is also the area where it is certified that a forest is managed in a sustainable way. More than 80% of sustainably managed forest in that terms, in the certified terms, is unfortunately in the Northern Hemisphere. So we need to bring this to the South. Regulations need to be adapted, but this is necessary. And I think if we think of this new forest strategy put out by the EU, that we have to put aside more land in order to serve for biodiversity. Yes, that's true. I think that a certain amount needs to be dedicated to biodiversity. On the other hand, if we don't trust in our sustainable forest management systems that we can do it both at the same time, sustainability, biodiversity, and products, including bioenergy, we will face massive leakage. And I think then we are behaving in the wrong way. So if we pretend that we are the rich North and we leave this task then to the South to deliver the necessary resources, then this is the absolutely wrong way. I think we can do better here, both from policy and also implementation perspective.
Sabine, do you want to intervene again? I had the impression.
No, I was just holding my head.
Look, yeah, okay. Look, exactly. I think we have to close. And I have to say, for me, it's almost impossible to summarize this so very rich discussion. But still, I will try. But I apologize in advance because I'm taking a very personal take here, which is deliberately a bit provocative and for your consideration in the next part of the conference. First, there is absolutely no doubt that bioenergy use must accelerate it, including in our IEA net zero scenarios. It has to triple in total terms from now to 2050, and it is very, very versatile with many co-benefits. And assessing and quantifying these co-benefits is complicated. Now, however, I think it is, and the presentation, which also emphasized that some scenarios, including ours, highlight that it is a limited resource, it is a precious resource. Probably it is not possible to apply bioenergy for all possible uses. And then I think for policy making, but also for the community, it is important to try to identify what are the priorities and what are the cascading system. What is the value of biomass that you have in a certain geographical zone, or maybe in a certain chain of technology conversions? And I would add, this was my answer to Annette's point, what are the alternatives? And in this sense, I would never use the argument, if you have more bioenergy, you will need less solar and wind. Solar is much cheaper than bioenergy, no doubt. For electricity production, I don't think this, rather I would say bioenergy is a very important complementary flexibility source to integrate more cost efficiently and more reliable increasing shares of variable renewables. If it is said in that way, I like it. But let's say when it comes, I don't know, to aviation fuels, it is a fact that aviation fuels have much less alternative. And so even if biofuels, advanced biofuels are very expensive, they're still very interesting. This is number one. Number two, it's the whole land use discussion. Because in the end, when it comes to the NGOs, the criticizer outside of this virtual room, this is one of the main point that they use. And I think that whatever the community managed to express, to demonstrate that managed land use are better than just conservation and don't touch anything, with good examples, and then of course discussing that, as you said, Florian, the Nordic countries is one thing and the tropical regions is a completely other story, but still, well, I think that this is a valid argument, because I've heard from some criticizers sometimes very extreme language of the fact that land use is under pressure from many sides, for food, for infrastructure, for whatever, illegal, whatever. Therefore, any marginal increase of land use is bad. Therefore, bioenergy is bad. And that's it. And the argument is closed. We collectively, when I say we, it's also the BioFuture platform, we are trying to have good language to respond to these very oversimplified statements. Now, I think for land use, it's also a very important point to ask what the right governance is, because there is another part which we have not touched at all, but which in tropical countries is incredibly important, which is the illegal land use exploitation and the lack of enforcement. This spending money from the north to the south to make sure that this is enforced, that would be a very good use of money in our part, in my opinion. My last 2 points. More emphasis on the bioeconomy. Many of you said it. It is not just about bioenergy. It is about the multiple uses of biomass. By the way, obviously in long lifetime products, the carbon is stocked for much longer. So there are many advantages which are difficult to assess, but this language needs to be fostered more. And I would encourage you during the work, IEA Bioenergy in general, I think you are doing a fantastic work in this direction. We collectively have to find as simple language as possible that is understandable for policymakers and for the general public. Always keep in mind the science, the facts, but in the end, unfortunately, this society decides on other, not very often on other consideration, and I think the effort needs to be done. Events like this are very helpful. Please don't get me wrong. I'm not saying that the fact-based and good analysis is not enough or not good. On the contrary, but the effort in having simplified language needs to go on and continue in this way. I wish to conclude by expressing, as always, a great appreciation from the IEA Secretariat for all the work that the IEA Bioenergy TCP does. It's amazing. Thank you for inviting us to this event, and I really congratulate, please, everybody online still join me in congratulating the panel, and many thanks also to Luke for organizing this and for assisting me in the moderation. Thanks a lot. Luke, I think you have the last word.
Okay, I really want to thank you and Jim also for moderating this session. And also a big thanks to the speakers, the 4 speakers. Andy's not here, unfortunately, because it's the middle of the night for him, but really appreciate your inputs, your presentations, and also your contribution to the panel debate. So big thanks. And just to close, for the participants who are still here, the presentations and the recordings of this session will be made available on the website of IEA Bioenergy a few days after the full workshop, actually. And we also invite you, if you haven't registered yet, I think it's still possible, we invite you to join the second session, which will be tomorrow, starting at 1 p.m. Central European time. So everybody's welcome to join that. And thanks again for your contributions to these sessions. So thank you.
Thank you. Bye-bye.
All right.